Hi students, Professor Nugent here. In this video, we are going to discuss the asymptotic properties of OLS. The discussion thus far has been with respect to the finite or small sample properties of OLS, and we've also derived some exact properties of OLS. And today what we're going to do is discuss the large sample or asymptotic properties of OLS. So what we mean is that we're looking at the properties of OLS as the sample size grows without bounds, so as the sample size goes to infinity. We are not thinking about any sample size in particular. So the first thing that we want to think about is the consistency of the OLS estimators. All right, so while not all useful estimators are going to be unbiased, consistency is going to be a minimum requirement. Consistency. So what is consistency? Let's use a figure to help us think about consistency. So for each sample size, say we're looking at estimating a slope coefficient for a given regression, and we have the choice of several different sample sizes. For each sample size, and I'll draw them in 3 different colors, the estimator is going to have a probability distribution that will be centered around the true population parameter because it is unbiased. And if it is consistent, what we're going to see is that the probability distribution becomes more tightly concentrated around the population parameter. So we may have a small sample that looks like this. Let's say N1 is the small sample. And then we get a little bit larger of a sample that looks something like that. That's N2. N3, maybe an even larger sample. And what you see is that the distributions are becoming more and more centered around the true population parameter beta 1. These are the probability distributions of the estimator beta 1 hat, and they're becoming more concentrated around beta 1. And as the sample size grows to infinity, what we're going to find is that this probability distribution is going to collapse into a single line on beta 1 as we reach infinity. All right, so this is the idea behind consistency, is that as the sample size gets bigger, the probability distribution of the estimator collapses onto the true value of beta 1. So let's define this in formal terms. Or we're going to prove it. The theorem is that under the first 4 multiple linear regression assumptions, MLR1 through 4, so we include all of the assumptions. We don't need homoscedasticity. We don't need the errors to be normally distributed here. So under the first 4, the OLS estimator beta hat j is consistent for beta j for all j, or j equals 0 through k, okay? So that's the theorem, and what we're going to do now for the rest of the video is prove this. Let's prove it. Good. So, proof. How do we prove this? Well, we're going to begin with an expression for beta 1 hat. Beta 1 hat is equal to sum from I equals 1 to n x1I minus x1 bar yi all over the sum from I equals 1 to n x1I minus x bar squared. And then let's plug in the equation for yi. This is equal sum from I equals 1 to n x1I minus x1 bar. Plug in the equation for yi, and we have beta naught plus beta 1 x1 plus ui, include the i's there, and this is all over the sum from I equals 1 to n x1I minus x bar squared. Now we can multiply through all of this stuff. The beta naught times this term, the beta 1 times x1I times this term, the ui times this term, so that we can get 3 separate terms. This is equal to, I'm going to need the full board for this. Oh my gosh, this is going to get huge. All the way over here. The sum from I equals 1 to n. Beta naught. Ooh, we want to put that, let's just put that in front, because the beta naught's not part of the sum, right? Beta naught is not indexed over I, so we're not summing over beta naught. We're just summing over x1I minus x bar, and we can bring this out. Sum from I equals 1 to n x1I minus x bar squared. Plus beta 1 times the sum from I equals 1 to n x1I minus x bar times x1I, right? So we had this term times this. We can bring the beta 1 out in front because beta 1 is not part of this summation. Beta 1 is being multiplied by everything, so we just bring it out in front of the summation. We are left with x1I times that term all over the whole denominator, sum from I equals 1 to n x1I minus x bar squared. Lastly, we have sum from I equals 1 to n x1I minus x bar times ui all over sum from I equals 1 to n x1I minus x1 bar squared. All right, now we're going to make a simplification. The sum from I equals 1 to n of x1I minus x bar, that is 0. So this term is going to fall out. That term is going to fall out. So we're going to be left with the two terms. And I want to spend a minute focusing on these two terms here, or really just this numerator. So I'm just going to erase this. And observe that the sum from I equals 1 to n x1I minus x bar squared, this is equal to the sum from I equals 1 to n of xi squared. We're just going to multiply this out. Xi squared minus 2x bar xi minus x bar squared. And we can, no, that's not squared. There's no parentheses there. Whoopsie daisy. Parentheses is there. So we can now bring all of this out into their own individual terms. Let them live individually. Sum from I equals 1 to n xi squared minus. Now observe that the 2x bar is not, we're not summing over 2x bar, we're only summing over xi, so we can do 2x bar sum from I equals 1 to n xi, and sum from I equals 1 to n over x bar squared, that's n times x bar squared. Okay, because we have n of the x bar squared. That's what when you sum over a constant, you get as many terms of the constant are included in the sum. So that's n times x bar squared. Now we can do some tricky stuff. What I'm going to do is, because we have here sum from I equals 1 to n of xi, I want to substitute in the mean here. So the mean, right, is 1 over n sum from I equals 1 to n of xi. So what I can do is multiply and divide by n up here, and then this term is going to become the mean. So let's do that. So that we have the sum from I equals 1 to n xi squared minus 2x bar times n times 1 over n. So I just multiplied and divided by n. That's like multiplying by 1. That's not changing the equation at all. Times the sum from I equals 1 to n of xi minus n x bar squared. Now this is equal to the sum from I equals 1 to n xi squared. And this is x bar, right? That's the mean of x. So we have minus 2 n x bar squared minus n x bar squared. So minus 2n x bar squared minus n x bar squared. Oh, this is a plus. This is a plus, right? All along that should be a plus. Something went awry. That is a plus. Yep, that is a plus. All right, continuing right along. We can collapse these terms so that we have the sum from I equals 1 to n of x1i squared minus n x bar squared. Well, observe that this is just equal to sum from I equals 1 to n x1i squared minus, we can also write this as x bar sum from I equals 1 to n xi, using the same trick that we just did a little while ago. And now we can write this as sum from I equals 1 to n xi minus x bar, right? Because you have 1 xi here, so we can factor out that xi so that you have xi minus x bar left. All of this to write that the sum from I equals 1 to n of xi minus x bar squared is equal to the sum from I equals 1 to n of xi times xi minus x bar. Okay, so I'm going to make this, adjustment in the numerator of the expression for beta 1 hat. I'm going to change this to this. And we'll start off the next video just that way.